Hello, this is Jack Jackson. We're going to be looking today at College Algebra Practice Test 4B. This will probably be the first part of this, and we'll break this up into a few videos. And let's dive in and start working this. I just brought this up. It says they're all marked wrong because I just pulled it up and got something so I would have access to this exam with the answers in it. So let's take a look at these. Number one. How much money will there be in an account at the end of 8 years if $11,000 is deposited at 3% interest compounded semi-annually? Okay, this is a compound interest type question. Guarantee that you'll probably see one of these on the exam and probably on the final exam too. This is a real basic type of example of applications of exponential functions. And notice the interest is compounded semi-annually. So we use the basic formula y equals y sub 0 times 1 plus r to the x power. We usually change the letters here. The amount in the account y is y. The initial amount is called the principal. And x is input is time, so we use t for time. Now the thing you got to remember about these is the time has to measure how often it's compounded. So if this is compounded semi-annually, t is the number of half years. Okay, in other words, twice the number of years. And of course then your r is your semi-annual rate, or your rate per half year. So we have to do a little conversion, but we'll do that in the formula here. So the principal is $11,000. 1 plus the rate. Now the nominal rate is 3%, so that's 0.03. But it's every half year, so we'll divide that 2 because we have 2 half years per year. In other words, if it's compounded semi-annually, it's compounded twice a year. So we have to divide that 0.03 by 2, and then the number of years is 8 years, but the number we have to multiply by 2 for half years. So that really makes the power 16. And this we can actually do pretty nicely. 1.015. So that was pretty easy to simplify a little bit in our head, but then at some point we're going to need to plug it in a calculator. So we can do 11,000 parentheses 1.015 to the power 16. If you want, you could have entered it in from the line above. 11,000 times 1 plus 0.03 divided by 2 to the power, and then parentheses 8 times 2. It's better to do that than to round it off. In this case, the rounding was exact, so it wasn't really rounding. So the amount, we're going to round off to the nearest penny in these kinds of problems because we assume the money is given exactly to the penny. So $13,958.84, and if you notice, that's what they have for their answer. Compound interest is a good example of exponential growth. A business estimates that the value of office equipment is decreasing according to a function v of t is 4,500 times 0.9 to the t. So you're keeping 90% of the value each year. You're multiplying the value of the previous year by 0.9, so you're losing 10% a year. So it's decreasing at a rate of 10% a year. That is not a continuous rate. That's the annual rate. So t is in years, and v is in dollars. Graph the function. Well, okay. So the first thing we're going to do is plug that in the calculator. So in general, when we get our formula and we have our calculator to do these problems, probably the first thing we're going to do is plug our formula in our calculator. Now we need to find a window, and since they give us a window, we want to match their window so we can see. Because we know basically the graph for an exponential decay function looks something like this, but we're probably going to be interested only in a portion of the graph right in here. So we need to use the window that they're using so we can match it to these, because otherwise we wouldn't be able to tell. So their window says start x at 0 and go up to 6 with a scale of 1, and y start at 0 and go to 6,000 with the scale of going up by thousands. And let's graph that. And now just looking at that picture, which one of these matches? Well, you can see the second picture there matches better than the first one. Now, we have two types of questions next. One where they give us an x and we want to find a y, and one where they give us a y and we want to find an x. So the first one is, what is the value of the machine after 2 years? They give us the x, we want to find a y. From the graph, we just hit trace, type in the x value we know, 2, and enter. And it gives us that point on the graph, and it gives us its coordinates. 2 years and $3,645. So the answer is the y value there, because they gave us the x. We can also do that, just to show you different ways you can do that. If you got it in as y1, you can of course go to here to get y1, parentheses of 2 years, and get the same value. We can do a table and make sure we have 2 in our table. There we go, and we've got our y value that way. Or of course, without, if you didn't type it in, then you could just go back to the formula, 4,500 times 0.9 to the power 2. And again, whoops, I put an extra 0 there. Okay, so again, you get the same thing. Okay, now if you want to do the second one though, there's a way to do this with logarithms. I'll show you how to do that in a second. But on this one, if we've got a graphing calculator, the easiest way to do it is to go here, and if we know the y, and we want to find an x, you graph the y equals a constant. So you graph 3,000 here for the second y, which will graph a horizontal line, and then we just want to find the intersection point. So you just do a calc intersect, number 5. And first curve is good, second curve, that's good. For the guess, put it close to where they cross, and enter, and this should give me a y value of 3,000, but an x value of it we're looking for 3.848359 years, and they say round it to the nearest hundredth of a year, so 3.85 years. Okay. Now, if you wanted to do this by hand, what we're doing is we're taking 3,000 and putting it in place of v in the formula, or in other words y or v or the output, and we can do it this way. So if you didn't have a graphing calculator, you could do it this way. You're probably going to need some kind of calculator though. Divide both sides by 4,500, and those will cancel out. So here we have 0.9 to the t. Let's see, this is divide top and bottom by 100, that's 30 over 45, then by 15, that's 2/3. Now, take the logarithm of both sides, and properties of logarithms say we can bring that out front, but then it becomes multiplication. And so t is the natural log of 2/3 over the natural log of 0.9. Now if you want an exact answer, there it is. But of course this is a real world problem. We're going to want a decimal answer. Then you're going to have to at least get a calculator at some point here and do this. Natural log of 2/3 divided by natural log of 0.9. Watch the parentheses there. And we got the same number that we got a while ago for x when we did it on our calc intersect. Okay, so you can do it that way. Personally, I would just do it with the calc intersect if we just need a decimal answer. Use the logarithm change of base. Now the change of base formula says if we have log base b of x, we can change that to any other base, say log base a of x, if we divide by log base a of the b. In particular, log base b of x is the base that we want to use is e, so this is natural log of x over the natural log of b. And so there's our change of base formula. So if we have log base 2 of 0.07, that's ln of 0.07, but then you divide by ln of 2. This one's lower, it goes to the bottom. And so we just do that on a calculator. ln of 0.07 divided by ln of 2, and this gives us our decimal approximation, negative 3.8365, which is what they have there when it's rounded to 4 places. Change of base formula. Of course, I derived that in the notes. Okay, the magnitude R measured on the Richter scale of an earthquake of intensity I is defined as R equals common log, base 10 log, of I over I sub 0, where I sub 0 is sort of a minimum intensity that they can measure for an earthquake. So if the intensity was given to be 10 to the power 7.25 times I sub 0, what's the magnitude? Well, the magnitude is R, which is log of I over I sub 0, so that's 10 to the 7.25 power times I sub 0 over I sub 0. Those cancel out, so this is log base 10 of 10 to the power 7.25. When you have these are the same base, they cancel each other out, and the only thing left is the power 7.25. So this is compared to this minimal intensity thing here. If you had intensity 0, I sub 0, this would be I sub 0 over I sub 0, which would be 1. Log of 1 would be 0. So a magnitude 0 earthquake compared to a magnitude 7.25, the 7.25 is 10 to the power 7.25 times as much on intensity, but the number only goes up to 7.25. So it uses a logarithmic scale there. Equation, 6 to the x equals 2 to the x plus 2. Okay, let me show you 2 ways to do this. First of all, I'm going to show you an algebraic way, which is probably not how I would do it here, but let's show you that first. So we take the natural log of both sides, and why do we do that? Well, because the property of logarithm says we can bring this out front as a power. If it's a power inside, it becomes multiplication outside. And so this is x plus 2 ln of 2. Distribute here, we got ln of 2 times x plus 2 times ln of 2. Here you have ln of 6 times x. Subtract ln of 2x from both sides. It leaves 2 ln of 2 on the left. And so we're subtracting out 2 ln of 2x from that side to get this to cancel. And over here we factor the x out, and we have ln of 6 minus ln of 2. And we divide by this coefficient on both sides to get x by itself, and we get 2 ln of 2 over ln of 6 minus ln of 2. Now at that point I can put it in the calculator. I can also do a little simplifying or changing around. This can come in as a power, so this is ln of 2 squared, that's 4. And I could write this as ln of 6 over 2, which is 3. So I could write it that way. So whether I write it as 2 ln of 2, notice parentheses around the numerator, divided by parentheses ln of 6 minus ln of 2, natural log of 2, we can get that. Okay, 1.2619, which is what they have here. Or if I did it as ln of 4 divided by ln of 3, hopefully that's the same thing, which it is. Now, of course, we have our calculators, which we'd have to have some kind of calculator to do the decimal approximation. But with the graphing calculator, we have something else that we can do. We can do this a couple of different ways on the graphing calculator. One way is to let y1 be the 6 to the power x, and let y2 be 2 to the power parentheses x plus 2. and then we want to graph it. Let me start with a zoom standard, but this may not be a good window. And we can actually, you can almost see it right there where they cross each other. Okay, and we can calculate that intersection. Let's make sure. Notice there's no negative y's, so I might as well start this at 0. Let me go up a little bit taller. We might be able to see a little bit better on that intersection. Okay, so right in here somewhere there's an intersection point. So I can do calc, intersect, first curve, enter, second curve, that's good. Get over kind of close to where they cross, that's kind of close, hit enter. And notice that's the same intersection point, 1.2619. Of course, these over here are exact answers, and that 1.2618595 is an approximation, but in this case they only want an approximation, so there you go. Another way to do this, and sometimes this works better on scale, is to put it all on one side and put 0 on the other side. So subtract 2 to the power x plus 2 from both sides. And now let me start with the zoom standard here, and we're looking for where this crosses the x-axis. Could be something over here, but it's probably an asymptote. Definitely right in there. Okay, actually it is an asymptote there on the left. And here we want to calculate the calculate the 0 this time, where it crosses the x-axis. So when you do this, it's asking for the left side, so get over kind of close, but on the left side, enter. Then it asks for a right bound, get on the right side, enter. And it asks for a guess, get it close to where it crosses the axis, and hit enter. And then notice again, it gives me the same x value that I had before. So there's a couple of different graphing calculator ways, and then an algebraic way. Of course, you don't have to do all those on the test. You can if you've got time to check things, but you only really have to do one of those. And of course, once we have an answer, we can check it by taking this value, 1.2619, that's approximate, store it as x, and do 6 to the power x, and these should be at least approximately the same thing, 2 to the power x plus 2. I did round off, so this is not going to check perfectly, but they check through several significant digits. If I'd used the non-rounded off version, they would have checked all the way. Alright, next, another application. The population of a city was 70,000 in 1992, and the exponential growth rate was 1.4% per year. Since it says exponential growth rate, that's k. So it tells us that k is 1.4%, which is 0.014, positive because it's growing. And that's per year, so time must be measured in years. And it says t is a number of years since 1992, so then this 70,000 is the initial amount. And so our population or amount, we're using the basic formula y equals y sub 0 e to the kt. P of t is y. The initial y was 70,000, so we'll go ahead and write that as 70,000. E to the power k, 0.014 t. Put that in parentheses, optional, or just make sure it's up in the power. And there is our formula, which is what they have typed in here. Of course, you're going to be using the palette over here to get the powers. Predict the population in 2006. Well, first of all, we need to find the t value. The t value is 2006 minus 1992, which is 14. So you have 2006 minus 1992, which is 14. And then we want to take this formula and evaluate. Now, there are a couple ways we can do it. I can just type it in like this with the t replaced by 14. I can also do it from the graphing, and I'm going to graph it because on part C I want to use the graphing. So 70,000, second ln is e to the power 0.014 x, close parentheses like that. Now let's see. Let's choose a window. We don't need negative x's. We're going at least 14 years in the future. We might want to go quite a bit more. Let's go 25 years. And y's, well, it starts at 70,000 and goes up. So I might as well just start at 70,000 or a little bit below, maybe 60,000. And then I need to go up from that. I need to go up at least 82,000. Here, let's go up 100,000. If we're going to do that, let's mark it off in 10,000s. Alright, let's graph that and see if the graph looks decent. Okay, good. So in part B, they tell us x and we want to find y. Well, they sort of tell us x. They tell us the year, and we figure out that x is 14, or t is 14. So we can do a trace 14, enter. And so here's the population, 85,156.883. Round off to the person, or 1,000. In this case, I say round it off to the 1,000, which is, of course, everything's rounded off to thousands, so that'd be appropriate. 85,000. When will it first be 82,000? Well, put the 82,000 here. Graph it. And then we just want to calculate that intersection. Again, I can do this. Enter first curve, enter second curve. Get close to the intersection. Enter. And it's 11 point something there. So I'm going to quit. There's my x. But to that I want to add 1992. And this says round it. So we're going to round it to the nearest year, 2003. Okay. Let's go on. Next question. Alright, so notice that if we have, if P is the proportion, or the part remaining, proportion, or percent, we'll change it to decimal, but the percent remaining, then what we notice is if we take that percentage, or proportion, that fraction, or decimal, times the initial amount, we get the amount that's there. But on the other hand, if it's exponential growth, one way to write it with the base e is y0 e to the kt. Well, the first thing we notice is we divide both sides by y0. That cancels. And so we get p equals e to the kt. So one thing this tells you is that if something's growing at a certain percentage rate, it doesn't matter how much you start with, the time it takes to double will be the same, or the time it takes to triple. Or if it's decaying, the time it takes for half of it to remain is the same, no matter how much you have. It's independent of the quantity there. So I'm going to solve this by taking the logarithm of both sides, or rewrite it as a logarithm. It's log base e of p is the logarithm, the power, kt. Now from here, we can solve for k is the log of p divided by t, or we can solve for t, it's the log of p divided by k. So it's probably useful to memorize that particular expression. Of course, you can derive it like this, again, pretty quickly on the test if you need to. Now, we have one problem where we're using the left one and one where we're using the right one. So country A, we know that their growth rate, growth rate K, and they tell us it's K, and they do mean the K that I use in class, which is the exponential growth rate here. And they know K, so we're going to use the one on the right. So to find the doubling time T, well, it's doubling time, so P is 2, because we're doubling. If we were tripling it, P would be 3. If we were doing a half-life, P would be 0.5. If we were trying to find the time until 75% remaining, P would be 0.75. And we just divide by the K. 0.025 per year. This is per year, so time is ultimately going to be in years. And of course we'll just do this approximately on the calculator. Natural log of 2 divided by 0.025, and that gives us about 27.726 years. And they say rounded off to the nearest year, about 28 years. Okay. On the other hand, the next one is backwards from that, so we're going to use this one over here. We know the doubling time, so P is still 2 because it's still doubling time, but we know the actual time, which is 27 years. And of course this will be per year for the units. And so this one is natural log of 2 divided by 27, and this is 0.025672178, or in decimals, approximately, in percents, approximately 2.6% per year. And that's what they have over here. So you can solve all kinds of problems about where we know the percentage remaining, okay, or proportion remaining. If it's 200% doubled, 3 if it's tripled, 0.4 if it's 40% remaining. We put that in for P, that percentage or that decimal, in a decimal form, and then we can either use this version on the left. If we know the time, we can find the K, or we'll use the version on the right. If we know K, we find the time, and of course it both comes from that. Suppose P is invested in a savings account in which interest K is compounded continuously. So they're talking about K. They did use the letter K. That's good. At 4% per year. Find the balance P. Okay, so unfortunately they use P here and they use principal here. I guess they should probably better call it P sub 0, e to the kt. And so if P is we don't know what P is, we just call it P. But if it's compounded, if K is compounded continuously at 4% per year, K is 0.04. So there's our formula for the amount, okay, which is what we type in here. Now, if we know that we invest $3,000, that goes there. And we're going to go for 3 years. So in these type of problems, compound continuous problems, this is 4% per year, that's 3 years, so those things cancel out. So we're going to work this out on our calculator. 3,000 times e to the power 0.04 times 3, close parentheses, enter. $3,382.49, which is what they have. That's good. When will it double itself? Okay, again, we're going to use the same kind of formula I used on the last problem. We know the log of the proportion remaining is K times T, so we want to find the time for doubling. So T is natural log of P over K. We know K is 0.04. We know we're doubling, so P is 2. So natural log of 2 divided by 0.04. Actually, since that's a single number, we can get rid of that. And we get about 17.3 years. Rounded to the nearest tenth of a year. Now, of course, we could have also done this by letting y1 be, actually it doesn't matter what you put in for P, but let's say it's 3,000 e to the 0.04x, then y2 just be double whatever you put here. So if that's 3,000, this would be 6,000, then just do a calc intersect, we'll get the same thing. Number 9, doll sold for $223 in 1980 and was sold again in 1987 for $451. Assume that the growth is in this collector's item was exponential. Okay, so this is a type problem where I'm given 2 points. I'm given 2 points. I'm given 1980 and 223, and I'm given 1987 and 451. So, if this is exponential, I could find the base by the formula y2 divided by y1 to the power 1 over delta x. y2 is 451, y1 is 223, and delta x is 1987 minus 1980, so that's 7. I just do that part in my head. So I'm going to do this on the calculator, and I'm going to store it as b in my calculator. Okay, so I can refer back to it. So 451 divided by 223 to the power 1/7, and let's store it as alpha b. So it's about 451, 223. Oh, they asked for k, not for the base. Okay, so that's the base. Okay, so there's our base. And the natural log of the base is k. So let's figure out k. So let's do the natural log of our previous answer, or b, and let's store that as k. Notice r, if we did r, it would be 1.1058, etc. But k is r is b minus 1. So let me show you that. So b minus 1, let's store that as r. So notice r and k are not the same thing. Okay, but they wanted k, the exponential growth constant, and so that was the 1.00613 whatever. Okay, so that is approximately 0.101 rounded to thousandths. Remember, it's tenths, hundredths, thousandths. That's 3 decimal places. Okay, keep going here. So what's the exponential growth function in terms of t? Where t is the number of years since 1980. So it's so then the 223 is the initial value. So we're going to use this one here, y equals y sub 0 e to the kt, because we know the initial amount is $223, and instead of y, let's call it v for value, t for time, and the k was, well, approximately 1.01 to the t. I'm going to actually put that in the calculator now, but I'm going to actually use the k and not round off. Let's hopefully this gives us what they have here. And then I'm just going to say alpha k x. So there's my, let's go ahead and say times x here. So there's my formula. The k is this 0.101, more or less. 0.101 is the rounded off version. Okay, if you see, that's the formula they have there with it rounded off. Estimate the value of the doll in 2007. So I can graph it and plug in 2007. Well, not 2007. I need to plug in the t value. It'd be 2007 minus. So first of all, let's figure out the t is 2007 minus 1980. So it's like that's 27. 2007 minus 1980. So that's 27 years from the beginning of this. So t is 27 on this example. Okay, and we want to find the time. So we can do y1. Let's see, I've got this calculator where I can go alpha trace and to get y1. So y1 of 27, we get that. And that's not what they have. Okay? The problem is, actually this is a bit, my answer is actually more accurate, but they've used it a rounded off version. So look what happens here. 223 times e to the power, if we use the rounded off version, let's see if this gives them, yep. So look how much difference that makes when you use a rounded off version in one of these things. The correct way to do it is to not round off until the final answer, and if you want to get it right on this problem, you need to use the rounded off version. So unfortunately they didn't do it probably the best way. They would both say 3,400, which is 2 decimal places of 2 significant digits, and when you round it off everything to 3 digits here, probably 2 digits is the best you can get on the answer here. But that's how they're wanting you to do it. So they're wanting you to do it with the rounded off version. So probably they're wanting to do the whole problem with the rounded off version, so we'll continue there. I'll show you how this works with and without the rounded off version here. So doubling time, again we use this basic formula, ln of p equals kt, and so the doubling time t is ln of p over t, where p is 2, and this is k. K is, now again, if we use, well, watch this. If we use the k in the calculator, ln of 2 divided by alpha k, which is the better way to do it, we get this value for the time. Rounds off to 2 digits, this is going to probably be the same either way, 6.9. If we use the 0.101 version of k, then it's natural log of 2 divided by 0.101. And notice these do agree to 2 significant digits, but not 3. This would be 6.89 would be more accurate than 6.86. But rounded off to two significant digits, 6.9 either way. So 6.9 years. Found the amount of time which the doll will be 3,961. Okay, so 3,961 equals, and they're going to be wanting to use the rounded off version, so let me go ahead and do that. We could do this with logarithms, or we could do it, with calculating an intersection on the calculator. If we're going to do this, again, I'll do it 2 ways. I'll do it with the k here. 3,961. Let's graph something here. Y's need to go from, let's see, 100 to, well, let's just go from 0 to 4,500. Go off 500s, let's say, and I don't know how far out we need to go. Let's go out 35 years. Alright, that's not bad. Okay, and we're wanting to find the intersection here. So calculate the intersection. And first curve, second curve. Get over here kind of close for the guess. And we get this, rounds off to 28.6 years if you use the non-rounded off k. However, if we use the rounded off k, which is what they're going to want, let me go back and change this to the rounded off version, 0.101x. Now do the same thing. Calculate the intersection. First curve, second curve, I'm going to guess 30. And now it's 28.5. So it does make a difference whether you round off in the middle. Unfortunately, this problem does it the wrong way. You're going to need to round off and then use the rounded off version to complete the rest of the problem. Not really the best way to do that. Next problem, according to Newton's law of cooling, a body with temperature T1 is placed in surroundings with temperature T0, different from that of T1. The body will either cool or warm to temperature T after capital T after lowercase t minutes by this formula. T, the temperature as a function of time, is your environment temperature, T0, plus the difference in the initial temperature minus the environment times e to the minus kt. Now the k depends on some of the properties of the object. Some objects cool faster than others depending on the properties of the object. So you could say put a potato in the oven and heat it up. This would be the oven. If the oven temperature stays constant, that would be the oven temperature. This is the temperature of the potato when you put it in, and there'd be some appropriate k, and we could work that out. Or we're having something that cools, like this example. We're taking a cup of coffee and put it in the freezer. So the temperature in the environment is 0 degrees. And the cup of coffee, when it's first put in, is 120 degrees. That's in Fahrenheit. And so we have this formula. Well, a bunch of zeros there, so we can simplify this to 120 e to the minus kt. Okay. Now to find k, we need some kind of ordered pair of lowercase t and uppercase t, a temperature and time. So after 5 minutes, that's little t, the temperature is 80 here. So this is going to allow us to solve for k. Divide by 120. Let me just go ahead and write that instead of let me write that the way we normally do it, the 5 first, then the k. Alright, let's see if we can simplify that. You can use your calculator if you want. 80 over 120 change to fraction, or you could easily do that one by hand, probably. 2/3. Rewrite as a logarithm. The natural log of 2/3 is negative 5k, so k is natural log of 2/3 divided by negative 5. Okay, so natural log of 2/3 divided by negative 5, and again I'm going to store that as k. Okay, so now our formula again is this. After 10 minutes, what will the coffee, what will be the temperature of the coffee? Here's our formula with that value of k. So it's 120 e to the power negative 1 times k times the time, which is in minutes, and then this will give us our temperature in degrees Fahrenheit, about 53 degrees. Okay. So this is kind of a transformed exponential function. Okay, here's another one that's a variation on it. This is actually a logistics function. In a town whose population is 2,000, a disease creates an epidemic. Number of people infected T days after the disease has begun is given by this function here. Graph the function. It is going to level out to an asymptote, and that asymptote will be 2,000, because as t gets bigger and bigger, this e to this negative power gets closer and closer to 0, so the denominator gets close to 1, the whole thing gets close to 2000. So it's going to have an asymptote of 2000. Logistics functions basically look like this, more or less, but we're only interested in a part over here. So let's go ahead and, in any event, they give us the formula, so we just put it in. Pay attention to our parentheses as always. So 2000 divided by 1 plus 22.6 e to the power negative 0.7 x. Close the parentheses on power, close the denominator 1. And let's get a window. We'll use their window so we can match the graph. 0 to 20 with a scale of 1. Y goes from 0 to 5,500 with the scale of 500. Okay, so let's just graph that. Okay, which one looks right? Okay, C is the one that looks right. Okay, how many are infected at time 0? Well, we can, now that we have this in here, just do trace and hit 0, enter, or do y1 of 0, or look at the table when x is 0, and that rounds off to about 85 people. So 85 people at time 0 were infected. How many infected is after 6 days? Do trace 6, and we get about 1,494. Okay, the next one, we want to solve an equation. 4 to the power x squared times 2 to the power 5x equals 8. Okay, and we want to work this out. We could try to solve this algebraically, but we could also just do it on a calculator. So on the calculator, I'm actually going to get 0 here and do 4x to the power x squared times 2 to the 5x minus 8. And we want to see where that crosses the x-axis. So I'm going to clear that out. I'm going to do 4 to the power parentheses x to the power 2 times 2 to the power parentheses 5x, close parentheses, minus 8, and I want this to equal to 0. So let me just start with the zoom standard. That's the nice thing about that, puts the x-axis in the middle of the screen. We want to see where it crosses the x-axis. Looks like we got a couple of places there. We can do a calc. Still graphing, okay. Calc 0, number 2, and let's find this one on the left first. So we want to go on the left side, move your arrow keys, or type in a number, but it's got to be on the left side. Okay, that's on. It's a little bit off screen there, but we notice the y is positive with it, so we're on the left. And then we go over here. That's on the right side. Put a guess somewhere close to where it crosses the axis, and enter. And that's a nice integer value, so -3 is one of the possibilities. To do the other one, we can do a calc 0 again. This time for left bound, we want to get over a little closer to it on the left side. Let's get past this little minimum here. Okay, that's decent. Enter. Right side. Okay, that's good. And then that's not bad for a guess. Enter. And we get 0.5. Now notice if we quit and type in x, that's the value, and we can say math, change to fraction. You probably knew 0.5 was 1/2, but if not, you can change it to a fraction like that. So x is an element of the set 1/2 comma -3, and they're just having you type in this part right here. Now if we were to do this by hand, you'd want to actually start up here, combine this together. We could do this with they have the same, I can make the same base by making 4 2 square. Okay, and so this is 2 to the 2x squared times 2 to the 5x is 8. So I can write it as 2 to the power 2x squared times plus 5x. And 8 I can write as 2 to the third. So since they have the same base now, I can just put the exponents equal 2x squared plus 5x equals 3. Get a 0 on one side, get a quadratic, 2x squared plus 5x minus 3, and we're going to try to use the property a times b equals 0 if and only if a equals 0 or b equals 0. So in other words, we want to factor this. Sort of anti-FOIL factoring. The only way to get the f of FOIL to work is to put 2x and x. And really our only choices are 1 and 3 for the L. So let's see, I believe we put 3 here and 1 here. Make this one positive, this one negative. I believe it'll work. Let's check it out. 2x times x is 2x squared. Negative 1 times 3 is negative 3. Here we get 6x minus 1x is 5x. And so then you either get 2x minus 1 equals 0 or x plus 3 equals 0. This says x equals negative 3. This says 2x equals 1, x equals 1 half. So x equals 1 half or x equals negative 3. Same answers we got the other way. So you could do it by hand or with the calculator. Let's do one more and then we'll stop the video and then finish the rest on the other video. So number 13, log base 4 of b plus 21 minus log base 4 of b plus 5 equals log base 4 of b. Okay, well, we want to get all the logarithms together into a single expression, and there's some hope since they're all base 4 and they need to have the same base. So there's some hope we can do that. I'm going to get a 0 on one side to get all the logs on the same side. Log base 4 of b plus 21 minus log base 4 of b plus 5 minus log base 4 of b. Now all of them have coefficient 1 or negative 1, so we can write that as one logarithm. And the ones that have b plus 21, they'll have a positive coefficient go to the numerator. The ones that have negative go to the denominator, so that's b, and this is b plus 5, and they're multiplied like that. Now rewrite this as an exponential. 4 to the 0 equals b plus 21 over b times b plus 5. 4 to the 0 is 1. Multiply both sides by b times b plus 5. And so I get b times b plus 5 equals b plus 21. Distribute here, we get b squared plus 5b equals b plus 21. That's a quadratic, so we get 0 on one side. B squared minus plus 4b, because we subtracted b from both sides, and then we're subtracting 21. So again, we want to factor this, b and b. Alright, what are our choices? We got 1 and 21 and 3 and 7 are really only choices. One will be positive, one will be negative. We want the difference to be 4. I think 7 and 3 is what we want there. And we want the 7 positive, the 3 negative. I believe that will work out. Let's check it. B times b is b squared. Negative 3 times 7 is negative 21. 7b minus 3b is 4b. So b minus 3 is 0, so b is 3. Or b plus 7 equals 0 in case b is negative 7. So 3 and negative 7 are our possibilities. Now, we do have to check them. Notice that on this side right here, you're taking the logarithm of b. So b has to be a positive number. So that's going to eliminate the negative 7. So that leaves only one left is b equals 3. Alright, what about a strictly calculator solution? Okay, well, we can put these in our calculator, but most of you don't have a calculator with log base b, so you have to use a change of base formula. We could do ln of x plus 21, but then you got to divide by ln of 4 minus ln of x plus 5, but then divide by ln of 4. And let's do minus ln of x divided by ln of 4. Now we want to see where this crosses the x-axis, so I'll do a zoom standard. Notice this is only going to be defined for positive x's. Looks like we got an asymptote coming down here, crosses there. I shouldn't even bother by putting in any negative x's because it's not allowed. And then I can do a calc 0, left bound. I need to get over into the positives now. There we are. There's 1. And then right bound. There you go. And get close to where it crosses there. We're closer to where y is kind of close to 0. Alright, hit enter. And x is 3. So b, or x is 3. So there's their solution. Alright, I think we'll stop there and we'll pick up with question 14 on our next video.